Our Sun is a loner, but in this it is unusual. Most stars are not solitary at all. They are born in gravitationally bound pairs, or in higher-order systems of 3 or more, and among the most massive stars binary membership rises toward a near certainty. A great many stars, moreover, visibly change in brightness over hours, days, or years. This chapter is about the physics that emerges when stars share an orbit, and when stars pulsate, erupt, or explode. These are not curiosities at the margin of astronomy, but two of its most powerful tools, for binary stars are very nearly the only way to weigh a star directly, and variable stars, through the steady beat of their pulsations, become the measuring rods by which we gauge the very scale of the universe. A binary star is a pair bound by mutual gravity, each orbiting their common center of mass. They are classified not by any deep physical difference, but simply by how we happen to detect them. A visual binary is seen as two separate points of light circling one another over years. An astrometric binary betrays an unseen partner by the wobble of the visible star. A spectroscopic binary is unresolved, but its spectral lines shift back and forth as the stars alternately approach and recede. And an eclipsing binary is oriented so nearly edge-on that the stars periodically pass in front of one another, dimming the combined light. The mechanics obey Kepler's laws applied to two bodies. The sum of the masses is fixed by the orbital size, and the period and the ratio of the masses by the relative sizes of the two orbits about the barycenter. The frustration is that we usually see only projected quantities, so a single method constrains a combination of the masses rather than each one alone. For a spectroscopic binary, the key measurement is the radial-velocity curve, the line-of-sight speed of a star, read from the Doppler shift of its spectral lines, tracing a periodic wave as it orbits. Only the component of velocity along our line of sight produces a shift, so the amplitude of that wave carries a hidden factor of the orbit's tilt. When only one star's lines are visible, the period and that amplitude combine into a single quantity called the mass function, and this quantity is a strict lower limit on the mass of the unseen companion. That makes it one of the most powerful tools in all of astronomy. A large mass function for an invisible companion is among the cleanest signs that the hidden object is a neutron star or a black hole. When both stars' lines are seen, their two velocity amplitudes give the mass ratio directly, but the tilt of the orbit remains the missing ingredient, and without it the individual masses stay just out of reach. That missing ingredient is supplied, beautifully, by an eclipse. A binary that eclipses must, by simple geometry, be viewed almost exactly edge-on, so the orbital tilt is pinned to nearly 90 degrees by the very timing and shape of the eclipses, and the masses fall out at last. The eclipse light curve gives still more. The durations of the dimmings, multiplied by the known orbital speed, yield the physical sizes of the two stars, and the relative depths of the deeper and the shallower minima give the ratio of their surface brightnesses, and hence their temperatures. An eclipsing, double-lined spectroscopic binary is therefore the gold standard of stellar measurement, delivering both masses to a % or 2 and both radii almost as precisely, with essentially no reliance on theory. These benchmark systems are the bedrock against which every model of how stars are built, and how they evolve, must ultimately be tested. When two stars orbit closely, a new geometry takes over. In the frame that rotates with the orbit, the combined pull of gravity and the outward centrifugal effect carve the space around the pair into a figure eight of teardrop-shaped regions, the Roche lobes that meet at a single balance point between the stars. A star that swells to fill its lobe can no longer hold its outermost gas, and matter begins to spill through that balance point onto its companion. This overflow is the master mechanism of every interacting binary. A star fills its lobe either by expanding as it ages off the main sequence, or because the orbit itself shrinks as the system loses angular momentum. And once the gas begins to flow, the entire future of the pair is transformed. The transfer of mass can even reverse which star is which, and the proof of it hangs in a famous puzzle. Algol, the demon star of the constellation Perseus, is an eclipsing binary of two stars, a hot, massive main sequence star of about 3 solar masses and a cooler evolved subgiant of less than 1. Yet this is a paradox. The two stars were born together, and heavier stars burn through their lives faster, so the more evolved star ought to be the more massive one, not the less. The resolution is that the subgiant was once the heavier of the two. It aged first, swelled to fill its Roche lobe, and poured most of its envelope onto its companion, reversing the balance of mass. What we see today is a stripped-down former giant beside a rejuvenated, fattened partner. the fingerprints of mass transfer written across the sky, and the very same physics that will later power nova and X-ray sources, turn now from pairs to pulsation. A whole class of variable stars, including the ones most precious for measuring distances, change in brightness because they physically swell and shrink, breathing in and out in a regular rhythm. What keeps this pulsation going against the friction that ought to damp it is a subtle engine called the kappa-mechanism, after the symbol for opacity. In most of a star, squeezing the gas makes it more transparent, letting heat escape and quieting any oscillation. But in special layers, where the temperature is just right to strip electrons from an abundant element like helium, compression instead makes the gas more opaque. That layer dams up the outflowing radiation, pressure builds beneath it, and it is pushed back out. As it expands and cools, it clears again and falls back, a valve that stores heat on compression and releases it on expansion, pumping energy into the pulsation on every single cycle, exactly like a heat engine. This engine only works when the driving layer sits at just the right depth, and that requirement carves out a narrow, nearly vertical band across the map of stellar temperatures and luminosities known as the instability strip. If a star is too hot, the crucial ionization zone lies too near the surface, with too little mass to drive anything. If too cool, churning convection carries the heat away and short-circuits the valve. Only within the strip does the driving zone sit, at the sweet spot, so any star whose life path happens to carry it across this band begins to pulsate for as long as it lingers there. And there is a clean relation underneath it all. The pulsation period is set by the star's density, with more luminous, more bloated, less dense stars beating more slowly. That single fact, bigger and brighter means slower, is the physical root of the period-luminosity relations that turn these stars into cosmic yardsticks. The grandest of those yardsticks are the classical Cepheids, luminous yellow supergiants, several to 20 times the mass of the Sun, that cross the instability strip late in life and pulsate with clockwork regularity over periods of days to months. Their magic is the period-luminosity relation, often called the leave-it law. The longer a Cepheid takes to pulse, the more intrinsically luminous it is. Because that link is tight and dependable, a Cepheid announces its own true brightness simply by the rhythm of its beating. And comparing that true brightness with how faint it appears reveals how far away it lies. Being so luminous, Cepheids can be picked out in galaxies millions of light-years off, which makes them the first and indispensable rung by which astronomy steps beyond our own galaxy into the wider universe. The relation was discovered by Henrietta Swan-Leavitt at Harvard, who studied Cepheids in the small Magellanic Cloud, all at essentially the same distance, and found, in work published around 1908 and 1912, a tight link between period and brightness. Yet the law can only measure distances once its 0 point is fixed. One must know the true luminosity of at least some Cepheids whose distance is already known. Pinning that scale down bedeviled astronomy for a century, until the European Gaia mission began measuring precise geometric distances to Cepheids in our own galaxy. There is a cautionary tale here, too. A second, older, fainter family of pulsators masquerades as Cepheids, and in the 1950s Walter Baade realized that Edwin Hubble had unknowingly calibrated the cosmic distance scale with the wrong kind of star. Correcting the error roughly doubled the distance to the Andromeda galaxy, and with it, the estimated size and age of the entire universe. The second great family of standard candle pulsators are the RR Lyrae stars, old, low-mass stars, more than 10 billion years of age, that have reached the horizontal branch of their evolution and happen to fall within the instability strip. They pulse quickly in well under a day, and crucially they nearly all share about the same true brightness, which makes them simple standard candles. Because they swarm in globular clusters and, throughout the ancient stellar halo, RR Lyrae stars are the premier distance markers for the old populations of the universe, complementing the young Cepheids that trace the star-forming spiral arms. More precisely, their brightness depends slightly on their chemical composition, giving a relation between period, luminosity, and metal content that is cleanest in the infrared. And this dependence underlies a long-noted split among globular clusters that took astronomers decades to understand. Because Cepheids define that first extragalactic rung, their calibration feeds straight into the measured expansion rate of the universe, the Hubble-constant, and into one of the sharpest unsolved problems in all of cosmology. There are two great routes to that number. The local route builds upward, step by step. Geometric distances calibrate the Cepheids, Cepheids calibrate the exploding stars called Type Ia supernova, and those supernovae reach out into the smooth expansion of the cosmos. This ladder yields a value of about 73 kilometers per second for every megaparsec of distance. The other route works from the infant universe, reading the expansion rate out of the cosmic microwave background, and arrives at about 68. The two disagree by around 5 standard deviations, far beyond what the stated uncertainties can excuse, and the gap has only hardened as the measurements have sharpened. The obvious escape was to blame the Cepheids. Perhaps in crowded and dusty distant galaxies, unresolved neighboring stars were contaminating their measured brightness and biasing the local ladder. The James Webb Space Telescope put that suspicion to a decisive test. With its far sharper infrared vision, Webb reobserved the very same Cepheids the distance ladder teams had used, and across 2024 and 2025, its distances agreed with the earlier ones, effectively ruling out crowding and dust as the culprit and confirming that the local measurement is sound. The tension, then, appears to be real and not a mistake in the stellar yardsticks. Whether it points to genuinely new physics in the early universe, to some unrecognized, systematic error, or to a flaw in our standard model of cosmology, remains wide open and fiercely debated. A frontier that a century of patient work on pulsating stars has brought into focus, but has not yet resolved. When a white dwarf, the dense, Earth-sized ember of a dead star, draws matter from a close companion, the result is a cataclysmic variable. The infalling gas carries too much spin to drop straight down, so it settles into a swirling accretion disk that slowly spirals inward, and where the incoming stream slams into the disk's rim, it lights up a brilliant hot spot. These are compact systems, whirling around in mere hours, and their fate is governed by how they shed orbital angular momentum. That physics leaves a striking fingerprint, a period gap, a curious scarcity of such systems with orbital periods between about 2 and 3 hours thought to arise when the donor star becomes fully convective, its magnetic braking falters, and mass transfer briefly shuts off, before the still-shrinking orbit brings the two stars back into contact once more. The most common eruptions of these systems are the dwarf-nova, which flare up by several magnitudes for days to weeks, and then subside over and over. Their outbursts are not nuclear at all but a hiccup of the disk itself. At low feeding rates, the disk cannot hold steady. The partial ionization of hydrogen makes its behavior flip between two states, a cool, quiet phase in which matter piles up, and a hot, bright phase in which the hoard is suddenly dumped inward, flooding the disk with light. Astronomers sort these variables by the character of their outbursts. Some show occasional extra-long, extra-bright super-outbursts, others only rare ones, others long pauses, called standstills, and by the strength of the white dwarf's magnetic field, which in the strongest cases seizes the accreting gas outright and funnels it straight down onto the magnetic poles, forbidding any disk to form at all. A classical nova is a far more violent affair, and this time the power is nuclear. Hydrogen-rich gas from the companion piles onto the white dwarf's surface, and the star's fierce gravity compresses it until the buried layer itself turns electron-degenerate, a state in which pressure scarcely responds to temperature. When the base of that layer grows hot enough to ignite hydrogen fusion, there is no safety valve. In ordinary gas, heating would cause expansion and cooling, but a degenerate layer merely gets hotter and burns faster, a runaway that builds explosively until, at last, the heat overwhelms the degeneracy and the whole shell is blasted off. The star flares by many thousands of times and hurls a fraction of its accreted matter into space at hundreds of kilometers a second. Crucially, and unlike the supernova that can destroy such a star entirely, the white dwarf itself survives. Because it survives, the cycle can begin again. Fresh gas accumulates, and in time the star erupts once more, blowing off another expanding shell of processed matter. How often depends on the white dwarf's mass and its diet. A heavy white dwarf with fiercer gravity needs only a thin layer to reach ignition, and so erupts more frequently, the recurrent nova flaring every few years to decades. Lighter or slower-fed systems build up for tens of thousands of years between eruptions and are seen to blaze but once in recorded history. The cast-off shells enrich the surrounding gas with the products of hot nuclear burning, and the deep question of whether a repeatedly erupting white dwarf is slowly gaining or losing mass bears directly on whether such systems might one day cross the fatal threshold and detonate as a Type Ia supernova, replace the white dwarf with something far denser, a neutron star or a black hole, and the same accretion becomes vastly more powerful, for the gas now falls into a far deeper gravitational well and releases enormously more energy, heating the inner flow to millions of degrees until it blazes in X-rays. These X-ray binaries are among the most luminous compact stellar sources in the sky, and their discovery founded the science of X-ray astronomy. The first cosmic X-ray source beyond the Sun was found by a sounding rocket in 1962, and the bright source Cygnus X-1, detected 2 years later, became the first object widely accepted to contain a stellar mass black hole. Here, at last, was observational evidence that the black holes of theory truly existed. X-ray binaries come in 2 kinds, distinguished by the star doing the feeding. In the low-mass systems, an ordinary companion no heavier than the Sun spills matter through its Roche lobe into a disk around the compact object. These are old systems, common in globular clusters and the galactic bulge. In the high-mass systems, the donor is a young, massive, hot star, and it feeds the compact object not by gentle overflow but through the sheer force of its powerful stellar wind. Cygnus X-1 is the very archetype of the second kind. Its black hole, gorging on the wind of a blue supergiant companion, has a measured mass of around 21 suns, among the heaviest stellar black holes known in our galaxy, and a stringent test of just how much mass a massive star sheds before it finally collapses. There is a natural ceiling to how brightly anything can accrete, called the Eddington limit, the luminosity at which the outward push of radiation on the infalling gas exactly balances gravity's inward pull. It works out to roughly 100 trillion watts for each solar mass of the accreting object, and beyond it the radiation would simply blow the incoming matter away. Yet what makes these systems so spectacular is their efficiency. The fraction of pure rest mass energy that accretion liberates runs to perhaps 10 or 20% for a neutron star, and from 6% up to over 40% for a black hole depending on its spin, figures that utterly dwarf the mere 0.7% released by the hydrogen fusion that powers ordinary stars. A compact object sipping matter at even a modest rate can therefore outshine a fusion-burning star of the same mass many times over. The variety of these systems is a laboratory in itself. A magnetized neutron star funnels the infalling gas onto its poles and sweeps beams across space as an X-ray pulsar, its ticking revealing the star's spin, and through the rhythm of the orbit its companion, rapid accretion can wind such a neutron star up to spin hundreds of times a second, linking it to the millisecond radio pulsars. A black hole, having no surface, shows no such pulses or surface flashes but cycles instead between hard and soft states as its disk and corona rearrange, often flinging out relativistic jets. And across every one of these systems the same simple measurement, the mass function, drawn from the companion's Doppler wobble, weighs the hidden object. And when that weight climbs securely past the 2 or 3 solar mass ceiling that no neutron star can exceed, it stands among the most reliable signs we possess that we are, in fact, looking at a black hole.